Okay, we are doing section 12.4a, problem number 21. And it's talking about the midpoints of the sides of a quadrilateral are being connected and the interior quadrilateral is obtained. So I want to draw that first on GeoGebra. And we did this first portion in class. Does anybody remember what that interior was? If you connected the midpoints of just a general quadrilateral.
Wasn't it a rhombus?
It was a parallelogram, wasn't it?
Well, we'll just go in here and see.
Actually, I think it was.
So I'm going to click on midpoint so we can get the midpoints of all of these sides. And now I'm going to connect the midpoints.
Oh yeah, I think you're right there, Susan. I think it's a rhombus.
Drag it. Is it staying a rhombus?
Parallelogram.
Yeah, it's a parallelogram. And does anybody remember why? We know that it's a parallelogram. I'll give you a hint. I'm going to put in a diagonal from D to B. So
Same
now
on both sides.
look at this big triangle, ABD, right here. The midpoints of that triangle are connected. Do you remember the midpoint connector theorem?
Is it something to do with symmetry?
If you connect the midpoints of a triangle, that mid segment is exactly half the length of the base of the triangle, and it's also parallel to the base of that triangle. So by the midpoint connector theorem, this segment right here, this mid segment, HE, would have to be parallel to that diagonal BD and half the length of it. But by the same argument, over here, you have another triangle where the midpoints are connected. So what could we say about this mid segment FG compared to BD?
Parallel.
Congruent.
To it. And also, how about the length of this one, the mid segment compared to BD?
It's congruent, right?
No, FG, what is that length compared to this diagonal here?
Would it be half the size?
It would be half as well, right? So because HE is parallel to DB and FG is also parallel to BD, we can say they're parallel to each other. And we also know they're the same length because they're both half the length of BD. And in a parallelogram, opposite sides are parallel and the same length, right? Does anybody remember that?
Vaguely.
Yeah, it's coming back to me.
Opposite sides have to be parallel in a parallelogram. So we just proved that opposite sides are parallel because they're both parallel to this middle diagonal. Okay, we could use that same argument. I'm going to take out this diagonal if we put a diagonal here from A to C. Now we have two other big triangles. The mid segment here is connected. So that segment would have to be parallel to AC and half its length. Well, by the same argument, this segment HG also has to be parallel to AC and half its length. Therefore, HG has to be parallel to EF So opposite sides are parallel and they are also the same length. So we know that we have a parallelogram if we just have a general quadrilateral. That interior figure is a parallelogram. And so when it says we have shown that MNPQ is a parallelogram, that's what we just went through. We know that it's that this interior figure, which ours is HEFG, is a parallelogram. What is the most you can say about the kind of parallelogram that interior figure is if ABCD, the outer quadrilateral, is a rhombus? So if our outer quadrilateral were a rhombus and all the sides were the same length, what could we say about that interior figure? So I'm going to just drag this into a rhombus shape. It's not a construction, but we can get an idea of that interior figure just from dragging this.
Is it that it still, I mean, it still remains a parallelogram, right?
Yes, but it's asking what special kind of parallelogram is it?
Rectangle.
If
Rectangle.
outer figure is a rhombus. And so what I'm going to do is measure these distances here. Oh, but when I'm dragging, I can get them the same. 'Cause we need a rhombus here in order to make our conjecture. The outer figure has to be a rhombus. So let me just drag this as best I can to get side lengths that are the same. Okay, we got 3.4 there. .4 on 3 other sides. That's pretty close. All right, so our outer figure is a rhombus. What is the inner figure? What does it look like to you?
It looks like a square.
Anybody else have thoughts on that?
The first sizing looked like a rectangle, but now I agree with Susan, it looks like a square.
A square or a rectangle? Is there a way?
Well, a square is just a special rectangle, so
So the question is it a rectangle or is it a square?
I
I
Oh,
feel
I
like
it's
it would be
square,
square if they're all the same.
yeah. Because
Like
everything's
our angles
congruent.
are all 90 degrees. Would it stay a square even if our rhombus were squished more?
If all the sides were congruent, I
All the
feel like it
sides of
would,
the
right?
outer figure are congruent. We do know that.
Yeah, then I would say that definitely. I mean, my response would be that it would be,
Let's see what we know. We do know all of these segments are the same because we constructed the midpoints.
So if you would only squish
side
A
angle
and
side,
B,
right?
Well, in a rhombus, the opposite sides are congruent. So we know this angle is the same as that angle. So these opposite triangles are congruent. And we would know that this side is congruent to this side. So those opposite sides would be congruent. But in a rhombus, not all of the angles have to be the same.
Well, you know, there's congruency with those triangles because of the side angle side.
Yeah,
Is that-
there's congruency with the opposite triangles, but not all four. Do you see what I'm saying?
Oh, with the angle, okay. Wait, for whatever reason, I was just thinking that those were all right angles, on the outside.
On the outer figure,
Yeah, that's what, and then I saw that you did those opposite angles and such. I just thought that
on the
incorrect.
outer figure, we're told that it's a rhombus, so the angles are not necessarily 90 degrees. It's just
Okay.
saying in any rhombus. So to me, because we have these opposite triangles are congruent, but not all four are congruent, that's convincing me that we've got these opposite sides would be the same because corresponding parts of congruent triangles are congruent,
So then maybe it is a rectangle.
and these are the same, right? So I am thinking that knocks out square. We can't say it's a square. We have shown opposite sides are congruent. The piece that's missing is we have to have all four 90-degree angles, which it sure looks like they're 90. But can we prove that they are 90? That's my main question right now.
Yeah, use that measure tool. I'm just kidding.
Well, we could use the measure tool, but I want to know for every rhombus out there. For every rhombus, can we say the interior figure is a rectangle? And why? I mean, we at least know it's a parallelogram because we have the opposite sides of the same length.
So you can figure out so now you can figure out the angles, right? Couldn't you figure out like the angle BFE? Because you've got your, hold on. Wait, maybe I thought too soon. Hold on. Because I was feeling like we could get that angle and then you could figure out what that side length is. Because you know,
This is my thought. Because we've got an isosceles triangle here, we know that these two base angles are the same. And by the same token, we've got an isosceles triangle here. So those are the same as well. I also am wondering if some part of this is because we've got a rhombus. Well, in any quadrilateral, all of the angles add up to 360 degrees. But in a rhombus, which is a special parallelogram, the adjacent angles add up to 180. So we know this one plus this one. Angle B plus angle C is 180. All of the adjacent pairs add up to 180. So can that help us in any way?
what I feel like you found the angle like CF, is that, I don't usually do this on my phone. CFB, if you found out that angle and then BFE, then you could find the angle for the inside of that rectangle to find out if it is 90 degrees, right? So is there something you could do with vertical angle? If you made a array out of one of those lines or segments?
Which segment again?
Well, I don't know. I mean, just any of them, because it's, it's all going to give you the same yield, the same response, right? So if you made one of those into array, then you could use the vertical angle theorem, right?
Like extend this one, you're saying?
Yeah. I mean, right? Couldn't you do that?
So
Because then
then
that would be,
vertical angles, this right here would be the same.
yeah, because the
BFE.
key is to find if that one is 90 degrees. So I feel like there's a couple different ways we can find those angles if you just extend that.
Hmm.
If those two. And then that would be the same as that. Well, I don't know. I guess that's in the same, we're in the same spot. Then.
Okay, and I'm gonna put a dot on these angles just to get the ones that are congruent here. So we've got an isosceles triangle there. So those two angles have to be the same. Therefore, and then we've got a congruent triangle here. So these would also be the same. But we also know that angle B plus angle C is 180. But these two dots plus angle C is also 180 because it's a triangle.
So, I mean, you can put the two equal to each other, but I don't think that that's going to find you a numeric value though, right? Wait, hold. That wouldn't find you equal value. That would just prove congruency, right?
The congruency is
confused.
proved from the side angle side.
Yeah. Well, you got me, Dr. Now.
Instead of calling them a dot, why don't we use a variable and call them, we haven't used an X yet, have we, in this whole thing?
No.
All right, so let's call these X. And then this one with the little 3 hashtags, let's call those Y. So we have a Y there and we have a Y there. And also on the other sides, we've got these are the same. We have Y and we have Y. All right, now I know angle B plus angle C has to be 180 because it's well, this is a special parallelogram, but we also know that 2x plus angle C is 180 because the angles of the triangle have to always be 180. Okay, so now I'm going to subtract C from both sides of these equations. So now I have 2x is the same as 180 minus C. And from this one up here, I have angle B is the same as 180 minus C. So angle B is 180 minus C and 2x is 180 minus C. So that tells me angle B has to be the same as 2x. So this one right here. And that's also telling me, now if I look at this triangle, if I add all three angles in that triangle, I would have y plus 2x, which would be 180, because 180 is the sum of the angles. In any triangle. So now I have 2x plus 2y has to be 180. And if I divide both sides by 2, oh, this is beautiful. If I divide this by 2, my 2's cancel here and here, I get x plus y equals what?
There's your right angle.
Equals 90. Okay. So if my x plus y here is 90, and this is along a straight angle, along a straight side, this whole straight side would be 180, but the x plus y is 90. Therefore, this angle has to be 90. And by that same argument, all of these other angles would have to be 90. Voila, we have proved it. We have a rectangle. Oh, I feel so good.
45, 40. Nice, well done.
All right.
Sorry, I asked about this one.
All right. So let's go a little more quickly through the rest.
Oh my
That,
God.
that one was a proof. We went through it. But now it's saying, what if your interior figure is a kite instead of just a rhombus? Then what do you have in the interior for part B? So a kite would be, and can I erase all of this writing on my figure? Because I want to drag the rhombus. I'm going to take a picture of this. This is too pretty, too beautiful to be left to just erased.
Yeah, my head hurts looking at that.
Or you can take a screenshot.
No.
Take a screenshot or a picture.
I just screenshotted it for myself.
Okay. All right. So now let's erase all of this. And now I'm going to get my move arrow. And to turn this from a rhombus into a kite, with a kite, you have two pairs of consecutive congruent sides. It looks to me like it's staying a rectangle.
I agree with you.
I agree.
Wait, isn't that something about how we've had problems like where the midpoint runs along that line and so it stays. I think we've had that on a question before, where if you change it, just moving it up and down that midline, it stays the same.
Where you take a point along here, you mean? Instead of the midpoint,
Yeah.
slid it.
Well, right. So you take that E and then oh wait, yeah. So that's not actually moving. So it's staying in the midpoint.
Yeah, this problem is, it specifically says the interior figure is formed from the midpoints. And so when we have a kite, it's again a rectangle. That's part B. All right, now it's saying, what if it's an isosceles trapezoid? What if this exterior figure is an isosceles trapezoid? So let's drag it to look like that. So we we need congruent sides and opposite bases parallel. So let me just try to drag that to get. All right, we've got 2.4 and 2.5 is, oh, there we go, 2.4 and 2.4. And our opposite bases, if the opposite bases are parallel, eyeballing it, it's pretty close. What do you think that interior figure is? What does it look like to you?
It looks like a rhombus.
I would agree that it looks like a rhombus.
I agree.
And I'll leave it to you to do the proof of that, but yes, it is a rhombus. And then the last one, D, it says, what if your outer figure is a quadrilateral that is neither a rhombus nor a kite, but whose diagonals are perpendicular to each other? And from our properties, if the diagonals are perpendicular, I know in a rhombus the diagonals are perpendicular, but it's saying it can't be a rhombus. Neither a rhombus nor a kite, but whose diagonals are perpendicular. What shape would you have to have?
Would you use your perpendicular tool on that? Or
It's
Or it could be a
the diagonals of our shape have to be perpendicular. So what I'm going to do is put on the diagonals. So here's our diagonals, and I'm going to measure one of those angles so that we can drag it to where they're perpendicular. Let me put on a point, sorry. Right now I'll measure it. Okay, so that angle right there, they're telling us has to be 90 degrees. So now I'll drag to where we get those diagonals to be 90. I've got it really, really close. What's it looking like to you?
It makes a rectangle again.
Looks like a rectangle. And it is. It is a rectangle. We are out of time, so I'll leave the proof to you, but you are correct. It drags into that interior figure would be a rectangle. Okay, well, thank you everybody for putting your heads together on a challenging.
thanks, Susan.
Yeah,
Yes,
and that's the most challenging,
yes.
challenging problem of the lesson. And if I put this one on the test, I would put a piece of the problem on the test. It wouldn't be the whole entire A, B, C, and D.
I think you make Dr. Knapp very happy, Susan. Oh, look at the baby.
Y'all have a great evening, and I'll look forward to seeing you on Tuesday.
Thank you so much, Dr. Knapp.
Thank
Have a
you.
good night.
Thank you.
Bye.
Have a good evening, everyone.
Bye, y'all. Have a good weekend.
Say bye.
Well, what's the dog's name?
Oh, Huck. Oh,
Huck?
Huck. Yeah.
There, Huck. Are you learning some math today? The smartest dog around.
So she's feeling better than Susan, right?
Yes,
She
he's feeling
was
much
real
better.
sick.
Oh,
She was
good.
real sick the other week, so better.
He says hello.
Okay. Bye-bye.
Bye.
Bye.